So, when we started this course on distributed computing, at that time I had mentioned that one of the advantages of having a distributed system is that there is redundancy in the system. So, if since there are many computing elements, so if some of the computing elements go down or behave in unpredictable ways, then the other nodes in the system can cover up for that thing. So, a distributed system ideally should degrade gracefully, in the sense that it should not be the case that if one node goes down or one link goes down, then the entire computation fails. So, fault tolerance is a very important concept in distributed systems, and we will start this by looking at a very fundamental problem in fault tolerance, namely the notion of agreement. Agreement in simple terms is like this, that I have a set of different processes and they try to agree on the truth of one proposition. So, or they try to agree on the value of one variable. Okay. Now, to agree on that, they have to communicate between each others, and we have to take care of the scenarios like processors going down while the agreement protocol is running, or processors behaving in a malicious way when the protocol is running, right. So, we will try to look at these kinds of scenarios, and under these different models we will study what are known as agreement protocols. So, first thing that we need to look at is, for fault tolerance we have two types of things, I mean two important parameters on which we can develop the taxonomy for these algorithms. One is the type of fault. So, we need to study the classification of faults, and the other is the type of redundancy or the type of tolerance that we want to define on that. Okay. So, the classification of faults can be they can be classified in two ways. One is based on the components that failed. So, it can be the failure of a program or a process, it can be the failure of a processor or the machine, it can be a link failure, that is the communication failure, it can be a failure of the storage, or it can be a failure of the clock. Okay, in the sense that clocks can go out of sync and you can have problems due to that. So, based on the behavior of faulty components, we have these types of faults. One is crash fault. A crash fault is a fault where the process which crashes or the processor which crashes, it just halts. So, that means that it stops participating in any further activity forever. Okay. So, that is the definition of a crash fault. Fail step is an extension of crash faults with some additional conditions, we will see that later. Omission is that the faulty component fails to perform some steps. So, otherwise whatever it does is not an invalid thing, but it exhibits incomplete behavior, that is, it does not demonstrate the complete behavior that is necessary for the component. Byzantine is the toughest of the lot. This is where the components behave arbitrarily. So, they can behave in a malicious way, right. So, what it is supposed to do, it will not do, and it will do something else instead. It will try to mislead the other processes. And then we have timing faults, where everything works as per the requirement, except that the timings of the events are not honored properly. The timing constraints are not honored properly. Now, let us look at the classification of tolerance. There are broadly two types of tolerance. One is masking, where the system always behaves as per specifications even in presence of faults. So, the fault is masked. So, that is one type of tolerance. So, you are going to say that up to so many of these faults, will not affect the behavior of the system. So, the final result that the distributed computation is computing will not be affected by so many faults. Okay. That is called masking. So, that many number of faults can be masked by the system, and there are non-masking cases where the system may violate specifications in presence of faults, but should at least behave in a well defined manner. So, that means that for these kinds of things we have two types of specifications. One is the specification which is the normal specification in the faultless scenario, and in the presence of faults we have a second specification which is weaker than the first, but the weaker specification must at least be satisfied. So, for example, when we talk about a vehicle or anything, if you have a tire puncture, okay, that is a fault which is not going to get rectified immediately, but the car should satisfy certain properties in spite of having that fault, in the sense that it should not turn upside down if one tire bursts in the while it is running, right. So, that kind of, that is what we mean by non-masking faults. So, there are some tolerance that has to be honored, even though the faulty system may not follow all the properties of the original specification. Beg your pardon? Masking means that we start the design of the system or the computation with certain specification. Okay. So, we say that at the end of the computation this specification must be honored, right. Now, what may happen is that the system may start having different faults, individual components may fail, okay. But in spite of that, the distributed system as a whole will continue to satisfy those properties, right. So, what do we mean? For example, you say that, okay, I have a system where I have redundancy, okay. Every decision is corroborated by two different agents, right. Now, if one of them fails, I can still arrive at the correct decision. So, that fault is masked. That is what is the meaning of masking of faults. Okay. Now, when a fault is masked, the two system, the faulty system and the original system, they are not completely equivalent, because this has a fault, this does not have a fault, but both of them satisfy the specification. Okay. Then we say that the fault is masked.
But we always require redundancy in any masking system. Some sort of redundancy would always be required.
In order to guarantee that you are able to mask mask certain faults, obviously there has to be redundancy. Now, that redundancy may not be explicitly pre-specified or pre-planned. The system as a whole might evolve and cover up for the faulty components. So, some of the components may do more computation and eventually arrive at the same solution. Is that clear? And non-masking means that certain faults are not masked, but when I say that certain faults are not masked, in non-masking fault tolerance, it is not, does not mean that there is no guard against faults. Certain types of faults can be masked, certain types of faults may not be masked, but for the ones which are not masked, even in the presence of those faults, the system should behave in some well defined manner. Okay. So, if specification A is normally supposed to be satisfied, now in the presence of these faults we say that, okay, we can't satisfy specification A, but it should still satisfy specification B. So, it should fall back on specification B whenever the fault is there. That is non-masking. Is that clear? A fault tolerant system should specify the class of faults tolerated and what tolerance is given from each class. Okay. Now, these are some core problems that are there in the area of fault tolerance. The most fundamental problem, as I mentioned, is agreement, that multiple processes agree on some value. The second problem is clock synchronization. I had mentioned this problem in an earlier class, where we want to synchronize the clocks, the physical clocks of more than one component. Stable storage is that during the computation at any point of time your storage, there are certain parts of the storage that should be retained, right. Like for example, when database transactions take place, halfway through the transaction, if the computer crashes, then we still have to recover from that and either abort or commit the transaction in the proper way. Okay, we are going to see more of this later. Now, what that means is that certain things will have to be backed up before you actually touch the real database, right. So, that to do that we need what is called stable storage. The stable storage means that even if the system crashes, that whatever you have put in stable storage will remain. Okay. Now, it is a non-trivial task to determine that how a computation should proceed and what it should back up in the stable storage, so that if there is a failure, it can go back to some consistent state of the system. Alright. So, we will study this in due course of time. Then we have reliable communication, point to point broadcast, multicast. So, these are again places where we have the need for agreement. Okay. Then atomic actions. So, again we will see this when we talk about database transactions and things like that. So, let us quickly, before we go into the algorithms, take a look at the results that are there for consensus. Consensus and agreement are roughly the same thing. I will come to it in more details later. So, let f be the number of faulty processors, then we have these tight bounds for message passing. Okay. So, we have two types of faults that we are going to study here. One is crash failures. Remember, crash failures means that whenever a crash failure occurs, that particular process is down for the rest of the computation. Okay. And we have Byzantine failures, where the process does not crash, but it starts behaving in some unpredictable or malicious way. Now, if you have f crash failures, okay, if f be the number of faulty processors, so suppose we have f crash failures, then in order to arrive at a consensus, the number of rounds that a protocol must have is at least f plus 1, okay, at least f plus 1. Is that clear? The protocol will have to have at least f plus 1 rounds of data or knowledge exchange to be able to sustain f crash faults. Okay. The number of processors has to be at least f plus 1, okay, and the message size is polynomial. Now, we will see there are algorithms, we will study algorithms which satisfies all three of these. So, not only are these lower bounds, we also have algorithms which can work in the presence of crash failures. We can reach consensus in the presence of crash failures with these bounds. So, these are actually tight bounds, because the upper bound of the algorithm coincides with the lower bound of the problem. Now, for Byzantine failures, where we have f faulty processes, the lower bound on the number of rounds is f plus 1, but the total number of processors that has to be there so that you can reach consensus in the presence of Byzantine faults is 3f plus 1. So, it means that if more or equal to 1/3 of the processors are faulty, then you cannot reach consensus if the faulty processors are Byzantine. In other words, if 1/3 of the processes are suffering from Byzantine faults, then you cannot reach agreement or consensus. Is that clear? We will prove all of these results, and again the message size is polynomial, and we will see there is an algorithm which achieves exactly this set of bounds, right. So, again these bounds are also tight, right. Now, let us go into the actual algorithms one by one and see how we
reaching consensus means that they all give out a valid result.
now it's reaching consensus is like this. Each of us has a value, okay, and we want to agree on a common value, okay. So, remember election is one kind of consensus, because everybody has his ID and we all want to agree on one leader's ID, okay. That leader's ID can be minimum, maximum, whatever, right. And the agreement and the election algorithm actually ends up by reaching a consensus among all the processes that who is the leader, right.
Why the message size? Why you take message size into use?
Message size will be an important thing. It's because you see, we also have to say that if this message size becomes too large, then the communication overhead will be high, right. So, with polynomial messages with so many rounds and so many processors, right. Now, remember that when we studied election algorithms, we never talked about faults, right. So, we assume that all the processes, they are hale and hearty and they actually exchange data as per the protocol. But here we are going to look at the consensus problem in the presence of firstly crash faults and then secondly Byzantine faults, right. So, they have to reach an agreement on the value, but in the process of reaching an agreement, some processes might fail, some processes might behave in malicious ways and things like that, right. Now, firstly let us look at an impossibility result, that consensus is impossible in the asynchronous case. So, if the processes are not synchronous, in the sense that we cannot synchronize them as per rounds and all that, then consensus is impossible, right. Even if we want to tolerate a single crash failure, and it is true for both message passing and shared read write memory, okay. In all of these cases, consensus is impossible. So, all the algorithms that we are going to study is for synchronous processes, right. Now, when we talk about synchronous processes, it does not actually mean that the physical clock of all these will have to be the same. It just means that we have certain synchronization points where all the processes will stop, synchronize and then move forward, okay. Clear? So, let us look at the consensus algorithm for crash failures first. So, this is the code for one processor, okay. What does it do? It takes my V is my input. What is my input? My input is my value, okay. That every process starts with its own value, okay. So, that value is put in V. At each round 1 through f plus 1. So, we will have f plus 1 rounds. If I have not yet sent V, then send V to all. Okay, it just sends V to all. Now, remember that this sending V to all is through individual messages to each of the other processes. Okay. So, it sends messages individually to all of them, and then wait to receive messages for this round. Then you wait to receive the messages for this round. If V is the minimum among all received values and the current value of V, okay, so set V to the minimum among all received values and the current values of V, and then if this is round f plus 1, then decide on that V, and if this is not round f plus 1, then go back here and again do this. Right?
So send V to all means all process or all something neighbors?
No, all.
And it's done in each round, sir. Every
In
round.
each round. So, let us see an example. Let us see an example. So, I have these processes 1, 2, 3. Okay. This one has a value of, let us say 5, this one has a value of 7, this has a value of 2, okay, initially, right. So, in the first round what happens, that this node sends the 5 to all the other ones, right. So, it sends 5 here and it sends 5 here. Okay. Now, this one sends 7, this one sends 7 here. Okay. So, these nodes, this were carrying 5, these ones are carrying 7, and this one sends 2. Okay. Now, at the end of first round what happens? At the end of first round, the value of 1, so that this is a V, is revised to the minimum of all the values that it has received. So, V becomes 2. Why 2? Because 3 had sent the value 2, and that is the minimum. It has got 2 from this, 7 from here, and its own was 5. So, 2. So, what will this one do? Okay. So, I have 3 processes, right, and let us say I have to know what is my value of f. So, suppose my value of f, suppose f is 2, then how many rounds do I have to go through? 3, because f plus 1 is 3. So, I will have to go through 3 rounds. This is round 1, then I will again do a similar round 2, and what will happen in round 2? They will all exchange 2, except 3. 3 will not exchange 2 anymore, because it has already sent 2, right. So, these 2 will exchange 2, 2, 2, 2, 2. Okay. Right, and then at the end of the second round, what will we have? Again V is 2, V is 2, V is 2. What will happen in the third round? No one will send anything, right, because they have all sent 2, and 2 is still their minimum value. So, nobody will send anything, right, and then after 3 rounds, so no one will send anything, and at the end of 3 rounds what is going to happen? They will all agree on the value v equal to 2. That's an interesting question. If you realize that in one level, in one particular round, if a process does not receive any message, then we have to understand whether it can decide there itself or does it have to wait for f plus 1 rounds. Okay. No. But so far we have not talked about faults. This is what happens when everybody is fine, that we did not have any faults, right. Now see, in this round there was no messages. Now suppose we have a fault. Okay. Now let us see what will happen in the faulty scenario. All right. So now let us see the values of V is 5 here, V is 7 here. So again in the first round this one sends 5, this one sends 7, and this one sends 2. Right. Now let us say that before, when it sent 2 to 7, before 3 could send 2 to 5, at this point of time, before sending this, it failed. So 3 is down now, 3 has crashed, right. So now tell me what is going to be the values of these at the end of the first round. What will be for 1, what will be V? Because it has got only 7, it has not got the 2, so 5. What will be the value of this one? 2, and this one has crashed, so it is out of the picture altogether. What will happen in this round? This one will send 2.
One will not wait for the value from 3.
No, because it knows that there can be failures, right. That is why you see, if you do not get a message from somebody, it can be 2 things. It is then you know that that person might have failed. Okay, so it is all synchronous. That is why we need synchronization. There is no waiting.
But there must be some upper limit for to which it will wait to cater for the maximum delay.
Now those are lower layer issues. How it determines the end of the protocol, end of a round, is a lower layer issue. So we assume that this is a synchronous system. So there is a fixed synchronization point up to which they wait. How that synchronization point is arrived at is not treated at this layer of the abstraction. Okay. So this is getting 2, and this one will it send 5 again? No, because it has already sent 5 in the previous round. So what will happen in the next round? This will remain 2, this will now become 2. Okay. And after becoming 2, now this one has got 2 for the first time, it has never sent 2 before. So, in the third round it will send 2. Yeah. So, if okay, so what was our f? See, our f was 2. Okay. Yeah, see, now this is a very important thing which you need to understand. The protocol needs to know f, right. F is not the actual number of faults that are taking place. F is the maximum number of faults which your algorithm can handle. All right. So, f is a parameter of the algorithm. It is a parameter of the algorithm. So, you anticipate that I am not going to have more than 2 faults, then you run the algorithm with 2 as the parameter value for f. Okay. So, you run the algorithm with f equal to 2. The actual number of fault may be 0, it may be 1, it may be 2. If it is more than 2, then your algorithm will fail to reach consensus. It may fail to reach consensus, right. So, f is not the number of faults really, it is the parameter of the algorithm which represents the maximum number of faults which this algorithm can handle, right. So, because f is 2, we will have to go into the third round. Yes. No, again you are confusing. F, it is one process which has failed. So, there is one fault that has happened. F is not that. F is a parameter of the algorithm. See, you do not know how many faults there is going to be there, right. So, how do you decide how many rounds to run the protocol? So, you choose a value of f without knowing how many faults there will be actually. How can you predict faults? You can never predict the number of faults, right. So,
in this case, if you choose f equal to 1, then you should be able to detect the failure.
If I had chosen f equal to 1, then I would have stopped here and see, with one failure they have actually reached agreement. In 2 rounds they have actually reached agreement, right.
Agreement but false, because the value of 2 was.
Now, why should it be false?
V is equal to 2 was, or this parameter v equal to 2, so was with the third node.
Yeah.
So that this agreement of agreeing on 2 is also.
No. The requirement is they have to agree on the same value, right, and that value has to come from some process, right. So, there are 2 issues here. One is validity. Validity means that the value that you agree upon has to come from some process. Now, at the end that process may or may not be alive. 2 is that the value that they all agree upon is a common value, that everyone agrees on the same value, that is the agreement condition. So, both of these are met, right. Now, you see, in this case the algorithm was being run with f equal to 2, which means we are just going to run 3 rounds. Even if there is no fault, we will run it for 3 rounds. If there is one fault, we will run it for 3 rounds. If there is 2 faults, then also we will run it for 3 rounds, because we do not know how many faults are there. It is a distributed system. Nobody, one process does not know how many other processes are going to fail.
Like error checking code, which you decide how much you can correct, how many bits you can correct. So if that's how many, this is how many faults it can handle, this algorithm.
Yes, this is a parameter. So, if you think that f equal to 2 is too less, then you will have to run the algorithm with a larger f. But remember that there is no point in keeping the number of rounds to be more than the number of processors, because there is that upper bound that we saw, the lower bound that we saw. Okay.
And so in the second and third rounds, they will 2 to 3 also. You just share the rest to.
Yeah, they will send it to 3 also. Okay, it will just everything is
Send to all.
sent to all. Okay. Now, is the algorithm clear? Right. Now, let us look at this. Let us look at the correctness of this algorithm. The first thing is termination. So, by the code we finish in round f plus 1, so no issues in termination. If you look at this code, there is no infinite loops or anything. So, it will just go through these f plus 1 rounds and terminate. Right. Second thing is consensus, that all active processes decide on the same value. We will prove this in the next slide. The third thing is validity. The value agreed upon is a valued value. So, again this is quite obvious, because processes do not introduce spurious messages. So, whatever value that you have received from some other process, that value has actually originated from some process. It is not that spurious values are coming. And if all inputs are the same, that if all of the values in all processes are the same, then that is the only value ever in circulation. So, if all the values were initially same, they will always agree upon that value only, right. So, this is the validity requirement, which is fairly straightforward, that the algorithm satisfies. Now, let us look at the agreement. So, suppose we look at the contradiction that Pj decides on a smaller value x than does Pi. Okay. So, we start by assuming that at the end of the algorithm, suppose we find that Pj decides on a value x which is smaller than the value on which Pi agrees. Now, that means that Pi did not get the value x, never got the value x, right, because if in any round it had got the value of x, then it would have taken min among all the values and then it would have become x, right, because in every node the values just decrease, they never increase. So, then x was hidden from Pi by a chain of faulty processors. Now, in the first round, okay, why did Pi not get the value x? Because the value x had originated from one process, that process has should have sent the value to every other process. Now, Pi did not get the value x, that means that in the first round the process which was sending the value of x crashed before sending the value to Pi. Is that clear? So, suppose Q1 was the process which was holding the value v in round 1, right. Now, it could not send it to Pi, because before sending it to Pi, Q1 crashed, right, but the value was definitely passed on to some Q2. Because at least one process must have that value x, otherwise how did eventually Pj get that value, right. Now, see that none of the processes which are active in the second round started with the value v. Why? Started with that value x. Suppose Q2 is active in the second round. Q2 did not have the value x in the first round, because if Q2 had the value x here in the first round, if Q2 had the value of x, it would have sent it to Pi, right. So, but Pi did not get the value x. So, Q2, it is not possible that Q2 had the value x at that point of time, right. Okay. So, Q2 got the value of x from Q1. Now, Q2 would have sent it to Pi in the second round, but Pi did not get it in the second round also. So, what do we conclude? That Q2 must have failed in the second round. In the second round, Q2 must have failed, right, because otherwise it would have sent it to Pi, but Pi did not get it. But again Q2 has sent it to some Q3, right. Now, what can we tell about the value of Q3? I can say that Q3 is getting the value of x for the first time here. Q3 did not get it in the second round, because if Q3 had got it in the second round, then it would have sent it to Pi, but Pi never got it. So, Q3 is seeing x here for the first time, right. Why? Because in the first round Q1 crashed before sending it to Q3, in the second round Q2 crashed, rather Q2 sent it to Q3. Okay. Now, we know that after f plus 1 rounds the algorithm had terminated, and even at that point of time x had not reached Pi, right. So, how many processes must have failed? F plus 1 processes must have failed. So, therefore, we conclude that this is only possible if f plus 1 processes failed, but that is a contradiction, because we are saying that at most f processes will fail. In other words, that if f processes fail, at most f processes fail, then the crash consensus algorithm will always reach agreement. Okay. We have shown that by contradiction, by saying that okay, let us say that at most f processes failed, but still Pj received a smaller value x than Pi. Okay. Now, then we saw that that is not possible, because this is only possible if x was hidden from Pi by a chain of faulty processes, but then that is only possible if there are f plus 1 faulty processes in this chain, which is a contradiction, right. So, that proves that the algorithm reaches agreement. Any questions on this? Is this clear? Right. So, number of, so we have worked this with f plus 1 rounds, okay, and what is the number of messages? It is of the order of n square v, right. Now, I leave it to you to see how we reach this figure n square v. Each of, what is v? V is the input set. So, it is the number of different values that are there. it is the set of different values that are there, right, and log v bits are needed to specify which value is there. So, this is the number of bits required to specify the value, the value v which is being broadcast. So, we need log v number of bits to represent that value, and if there are v different values, then we will have n square v messages, because you see, if there is only one value, then after the first round no further messages will be exchanged, right. If there is only one value, then in the first round everybody will send that value, in the second round they will see that it is the same value, so they will not send it again, right. So then you just have n square values, n square messages for only the first round, each one sends to n of the other one, so order of n square messages in the first round, right. If there are v different messages, now how do we get this v there then?
All is in a different
As and when the main message is there, it stops sending. Next every subsequent round it will not send.
What is the worst case scenario for sending these messages? You have to first understand that. The worst case scenario of these messages. So, first of all, okay, if there is no faults, no, if there is no fault, right, after the first round everybody will get the minimum one, in the second round they will broadcast the minimum one, third round onwards no more messages, clear, right. So, it will be 2n square if there is no fault, n square in the first round, n square in the second round, then no more messages. Now, then what is the worst case scenario? So, the minimum value, see, what may happen is, in every round a new value is being broadcast, becomes the minimum one, and the smaller ones, because of the faults, they are not propagating to everybody, right. Okay, I have given you enough hints. Now you should be able to.
just send to the next higher value process and it will fail, and it won't send the rest of the process. Again, the same will happen with the next higher value process. It will send to just its higher value process and will fail.
Right. So I think you should be able to work out and show that it is, in the worst case it will take n square v messages. All right. So with that we will stop here today.